So my name is Sebastian. I work at TU Darmstadt as a PhD student at a scientific computing group. And I'll be talking about using link-time call graph embedding to streamline compiler-assisted instrumentation selection. And I'll get into what I mean by that. But first, I want to give some background on my work. So I'm involved in and partially funded by the XRay project, which deals with the exploitation of exascale systems for open source computational fluid dynamics. And the main software there is the OpenForm toolbox for CFD, which is a commonly used CFD solver in industry and academia. It's a quite large code with over 2 million lines of code. And the goal of this XRay project is to prepare the software for exascale simulations and for next generation HPC systems. So there are several packages in this project. Some are implementation of new features or improvement. So for example, development of new solvers, better parallel I/O, load balancing, porting to GPUs and that kind of stuff. But I'm involved in the co-design, profiling and performance analysis part of the project. And the goal there is to continually assess the performance of the existing project and of new developments. And a central thing that we are trying to do is to build empirical performance models. So we are running small-scale experiments on our clusters and then collect performance data and use that to extrapolate the runtime to find possible issues when running larger simulations. So for that, we need to collect reliable performance data. And there's basically two methods for that. The first one is sampling, where you interrupt the program periodically and examine the current state. And this is more statistical in nature, and it's very good for overview measurements because it's easy to apply. But the data that you get is statistical in nature, so not too reliable if you're interested in fine-grained data. So the other method is instrumentation, where you modify the program to measure code sections directly. This can be done either on the source level, on the IR level in the compiler, or even at the binary level. So with instrumentation, you get better control and more reliable data. However, there's a caveat, and that's the overhead management. Because if you just instrument all functions in the project, then the runtime just explodes in many cases. So what you often have to do is filter out functions that are not needed and that contribute most to the overhead. And there are several methods how you can do that. The first one, and I would say the traditional one, is the manual filtering, where you first perform a full instrumentation of the project and then examine the profile and build a filter list manually. Then there's tools that allow what I call profile-guided selection, where it's basically the same thing, but the building of the filter list is done automatically based on execution times, call counts, or memory requirements using some heuristic. And what I'm mainly interested in is this third category, which is compiler-assisted instrumentation selection, where we try to combine static analysis and user direction. So because for the profile-guided approach, it's quite usable and makes sense, but the main problem is that it ignores the context of the functions, of the function calls. So there might be issues that functions may be excluded that you actually want in the measurements, or the other way around, that there are whole regions of codes that you don't need, but that are measured anyway because that's not built into the profile-guided system. So we're trying to use static analysis to have a more intelligent approach for that. And the goal is to enable selection based on the call context and code features. And by code features, I mean For example, the expected complexity or runtime of each function can be just instruction count, or if there's loops in the code that can be integrated into the decision. So for that reason, we have developed CaPI, which is short for Compiler-Assisted Performance Instrumentation. And this is an instrumentation tool that is based on an older project called Instro. And I won't get into the details what differentiates the two projects here. But we have an upcoming paper at a workshop at ISC this year. So if you're interested, there's more information there. But in a nutshell, it uses a pipeline of configurable selection modules specified using a custom DSL. So the user can chain these selection modules together. And each of these modules has access to a central whole program call graph, which is the central data structure here. And this call graph is built by a tool called Mtg, which is a Clang-based tool that runs on source code and builds a whole program call graph. To give an example how CaPI works, here's an example selection pipeline for measuring MPI communication. On the left here, there's a main selector and an MPI selector. The main selector just selects the main function, the entry point, and the MPI selector selects all MPI function calls. And then the call path selector finds all paths between the main function and each MPI call and selects all of these paths. Then there's the option to combine this further with, for example, an inline selector where you subtract all functions that are inlined, or a name selector where you just exclude certain functions by name. And there's more possibilities, of course. So here's a more detailed look into the toolchain. We have a separate analysis and selection phase where we first put each translation unit into a Mtg, which then builds a local call graph of the translation unit. And at the end, we merge them all together into one whole program call graph. We then use this call graph to run our CaPI analysis with the selection specs supplied by the user. And at the end, we get an instrumentation configuration, which basically is a list of functions that we want to instrument. We then put this instrumentation configuration into our compilation chain. And then we have a custom instrumentation plugin that inserts the instrumentation for our measurement interface. In this case, we use CaPI as our measurement library, but you can use different libraries. So the results we had were pretty good with this toolchain. However, there are some usability issues, especially if you're working with large programs such as OpenFOAM. So the main thing is that the whole program analysis has to run before the compilation, or currently does run before the compilation. So it's a whole separate step, which is time-consuming, not only to run, but also to set up, because in essence, you sort of have to mirror the whole build system. Another point is missed calls due to defects in the call graph. That may be due to bugs in the analysis, but also simply because there may be function pointer calls that cannot be resolved, so you don't always have all the edges. And so you can't really rely on the analysis to be complete, and you sort of have to validate your profile that you get at the end to not miss anything, which can be cumbersome. Also, a separate point not related to the analysis is the maintenance of multiple configuration, which requires separate builds, which wastes space and is time-consuming for large codes. So, what we're trying to do now, and what's the topic of this talk, is shifting the workflow. We're trying to fully eliminate this whole pre-processing step, and we are doing this by running the call graph analysis at compile time. So for that, we can't really use the normal optimization pipeline with a plugin because we need a whole program view. And that's why we use link time optimization to run this analysis. Of course, this also means that the call graph is only available after compilation. So we can't do a static instrumentation because information is simply not there. Instead, we do dynamic instrumentation at program start, where we take this call graph and run our CaPI selection at program start, and then perform dynamic instrumentation. And LLVM has a project called XRay, which is perfect for this, which basically allows to do dynamic instrumentation and insert handler function for function enter and exit points. And at runtime, what we also now can do is use this call graph that we now have available to do some validation. For example, to check that that all edges are consistent between the static call graph and the call chain that we actually observe at runtime. So this is how the new toolchain looks like. So we now have compile time and runtime now pre-processing. At compile time, we take all these different object files, and at link time, we have a plugin that does the call graph analysis, and the results of that is serialized and embedded into the binary. So for each executable and shared library, we have a call graph that is sort of whole program, but of course, if you're using shared library, not completely, but it's combined of several translation units. Then at runtime, we can load this call graph and merge it with remaining shared library call graphs, and then run our selection and the dynamic instrumentation. So what are the benefits of this new system? So like I said, we have no separate analysis phase now, which makes it much, much easier to use. We can change instrumentation without recompiling. We can do validation with inserted checks in the IR, and do incremental refining of the call graph using runtime information, for example, if we have unresolved pointer calls. So a few words about the implementation. For the call graph analysis, we use a modified variant of LLD because the upstream LLD does not support plugins currently. So we have a version that allows that. For the call graph analysis, we are based mostly on the LLVM existing analysis, but augmenting that with inheritance information that comes from a vtable analysis, which is partially based on the Phaser project, which is a static analysis framework for LLVM. And we use the same MetaCG format that we used before, just a different analysis. For the embedding, the plugin inserts a global variable where we serialize the whole call graph and just put in the whole string. And we also add an initializer to the global CTOS to pass the call graph to the runtime system. So for dynamic instrumentation, we use XRay, which is a tool which was initially developed by Google for performance monitoring and tracing, and which was integrated into LLVM, although as far as I'm aware, there's no active development at the moment. So this can be easily activated with flag XRay instrument. And what it does is inserting no obslets into at function entry and exit points, which can then be patched at runtime. And the handler functions that are called can be replaced with a custom measurement interface. So I should say that we have a prototype that's very early. So we have done some evaluation, but it should be taken with a grain of salt. And for that we used the proxy application Lulish, which is an application for shock hydrodynamics. And we had some really good results with that so far. So the overhead is for initialization is below 1 second, and that involves loading the call graph and running the CaPI analysis and patching the functions. And when running with the inactive binary, so where XRay has been applied but not the functions haven't been patched, the overhead is below 1%, which means it can be possibly used in production without penalty. And the instrumented version is comparable to a version that uses normal static instrumentation, so there's not really any difference there. So to conclude, we have eliminated the pre-processing stage in CaPI using link time call graph embedding combined with dynamic instrumentation, which led to increased usability and better validation possibilities. What's currently missing and what we may need for OpenFOAM is support for instrumentation of shared libraries, which XRay currently does not support. And that's the end of my talk. Thanks, and I'm happy to take questions.
Well, thank you very much, Sebastian. Do we have any questions out there? Raise your hand if you have one.
Thanks for the talk. It was really good. So my question is, have you considered embedded the call graph in a separate section rather than global variables? Because after you finish the instrumentation using XRay, you can just unload the section.
Oh, that's a good idea. I haven't thought about that.
Yeah, because that is how LLVM embedded the big code.
Yeah.
Yeah. Like
we can have a discussion about that. That might be a good idea.
Yeah. You're using ELF, right? Yeah.
Yeah.
Thank you. Any other questions? I have one. You mentioned selection criteria once loaded to select, is that where to put the instrumentation or what instrumentation to activate? Do you have any examples of what selection criteria might be chosen?
So one of the examples here is what we're using for OpenFOAM oftentimes, at least part of it, is the MPI selector. So you most of the time the call path that you're interested in also use MPI. So you're trying to instrument those. And here we take just all functions that call MPI and then select the whole call path up to the main function. That might be a criteria here. And there's more involved stuff. For example, you can also do what's called statement aggregation, where you take a function and count its instructions in IR, and then combine that with all the instruction counts of each function call below that. So you have sort of an accumulated idea of how long this function might take, so very roughly. And you can take that as a baseline to decide whether you want to eliminate this function or not.
And we have one final question here, if it's quick.
So you say before that OpenFOAM has around 2 million lines of code.
Yeah.
Lulish has around like 5,000. And you say you need a whole program view for your analysis. Do you have an idea or a pathway to scale it? So is your LTO plugin already parallelized, or is it serial? And how do you want to scale this up to?
Yeah, that's something we have to work on. So for the moment, we are just working with like simple proxy applications to get everything right. And yeah, that might be something that will cause more overhead. But yeah, at the moment, I can't really say much about that.
Well, thank you very much, Sebastian. We'll set up for our next speaker in a moment, but let's thank our speaker here again.